Welcome to The Explainer. Every single time you tap your phone, or click your mouse, or do, well, anything with a computer, billions of tiny decisions are being made, instantly. But how? Well, it all boils down to one brilliantly simple idea: the logic gate. Today, we're going to pull back the curtain on the tiny switches that literally power our digital world.
Really think about that for a second. How does a machine think? Your computer is making billions of little choices right now just to show you this explainer. It can feel like magic, right? But it's not. It's actually pure, simple, predictable logic. So let's see how the trick is really done.
And here's the answer. It's this: the logic gate. The best way to think of it is like a microscopic security guard. It sees electrical signals come in, checks them against a single, very simple rule, and based on that rule, it decides whether to let a new signal pass through. That's really it. Every amazing, complex thing your computer does starts with that one simple decision.
Okay, so to understand the rules these little gatekeepers follow, we first have to learn the language they speak. And good news, it's pretty much the simplest language in the entire universe.
Yep, this is the entire vocabulary. Binary. Everything from sending an email to rendering a complex 3D world in a game is just a really, really long string of these two signals. A 1 means on, and a 0 means off. That's the language. And the logic gates we're about to meet, well, they're the grammar. They're what turns those two simple words into a masterpiece.
So, with that in mind, let's meet the key players. You can think of these as the essential letters in the alphabet of all digital thought.
All right, I know. At first glance, this might look like some kind of weird alien hieroglyphics, but don't worry about memorizing these symbols. We're going to walk through each one, and I promise you'll see that the rule behind each of them is incredibly simple.
So let's start with the big three. If this were a family, these would be the founding members. Almost every other kind of logic is just some combination of these three fundamental gates: not, and or.
First up, we have the NOT gate. That's the one that looks like a triangle with a little circle at its tip. This one is the ultimate rebel. It has one input and one job: to do the exact opposite. You send in a 1, it outputs a 0. You send in a 0, it spits out a 1. Simple as that. It's a pure inverter.
Okay, now find the symbol that's shaped like a capital D. That's the AND gate. Think of this one as the really strict bouncer at an exclusive club. It will only, and I mean only, output a 1 if input A and input B are both 1. If even one of them is a 0, nope, the output is 0. It is all or nothing.
Now find the one that looks kind of like a curved shield or a rocket tip. That's the OR gate. And this one is the total opposite of the AND gate. It's super relaxed. If input A or input B is a 1, it's happy to output a 1. The only way you can possibly get a 0 out of this gate is if you give it nothing but zeros.
All right, so you've got the basics down. Once you get not, and or, the rest are basically just clever remixes of those three. Let's take a look at these combinations.
So this is the NAND gate, and you can probably see it's just that D shape of the AND gate, but with that little not circle at the end. The name, NAND, literally gives it away. It's a not and. It does the exact opposite of our strict bouncer. The output is always a 1, unless both inputs are 1. Then it's a 0.
And I bet you can already guess what the NOR gate does, right? You look for that curved OR symbol, again with that little circle on the end. It's a not OR. It completely flips the behavior of our friendly OR gate. This gate will only output a 1 if and only if all of its inputs are 0.
And finally, find the one that looks like the OR gate, but with an extra curved line behind it. This is the XOR gate, which stands for exclusive OR. Now this one's really interesting. It's basically a difference detector. It only outputs a 1 if its inputs are different from each other. So a 0 and a 1, you get a 1. But two zeros or two 1s, you get a 0. This one or the other, but not both rule is absolutely critical for things like digital math.
So we've met the whole family now. But you might be wondering, how do engineers keep track of all this, especially when they start wiring hundreds or thousands of these gates together? Well, they use a really simple but incredibly powerful tool.
This is called a truth table. It's basically the ultimate cheat sheet for any logic gate. This one right here is for our strict AND gate. See how it just maps out every single possibility? If input A and B are both 0, the output is 0. If one is 0 and the other is 1, still 0. It's only on this very last row where both inputs are 1 that we finally get a 1 on the output. It's a perfect, predictable map of exactly how that gate will behave.
Now this is where things get really wild. Look at these truth tables. The first one, for just 2 inputs, has 4 rows, right? 4 possibilities. But look what happens when you add just one more input. The table for 3 inputs suddenly has 8 rows. And the one next to it, with 4 inputs, 16. It needs 16 rows. With just 4 simple on-off switches, you already have 16 unique states to manage. This right here, this is the secret sauce: exponential growth. It's how you get from a handful of dead simple rules to mind-boggling complexity really, really fast.
And that's really the core idea to take away from all this. Each individual logic gate is, well, kind of dumb. It's just a predictable switch following one simple rule. But when you connect billions of them together, you get this: the seemingly intelligent, deeply complex behavior of a modern computer. An entire universe of complexity, all born from simple yes or no answers to simple questions. It really makes you wonder, doesn't it? Is that all our own intelligence is too? Thanks for watching.